Good evening, everyone. Welcome to the Amateur Radio Technician class, session number 3. This is our agenda for today. We will go through what we covered during our last session. We will also have a look at our progress as it relates to the curriculum. We will briefly again talk about the practice exams. We'll have a question and answer session from questions posed between the last session and now. Then we continue with our technical material, and we are still in the electrical principles section of the course. Subsequently, we will tackle all of the questions in the question pool that relate to the theory that we would have covered today. And then we will announce the next session. Right, so our previous session, we looked at our curriculum progress. We talked about the practice exams. We had a Q&A. We discussed what exactly is electricity. We had a look at the electric circuit and the water analogy. We discussed voltage and current. We differentiated between direct current and alternating current. We discussed the concepts of resistance as well as conductors and insulators. We went into what Ohm's law is, and then we did some example calculations using Ohm's law to find resistance, current, and voltage. Then we followed by a question pool review that looked at all of the questions relating to all of the theory that we had covered. Then we mentioned about an upcoming webinar. We provided the contact information for participants if you needed to ask any questions. And of course, we discussed the date for the next session. So when we look at our curriculum, we see that we are in early days yet. We are on the first topic, electrical principles. So we have quite a ways to go again for us to complete the course, but we are making good progress. Just a reminder that practice exams are available, and we are hoping that all students would take advantage of the practice exams. So let's now get a bit into the Q&A. All right, so the first question that we had was, do I have to take the exams? So it's really up to each participant to decide if you wish to take the exams, and if so, when. We do not obligate anyone to take the exams. However, we are really hoping that each and every one will consider taking the exam. I mean, after you do the course, become knowledgeable, hopefully you would have understood all of the material. And by taking the practice tests, you will gain the confidence that this is doable, this is within your reach, and consider taking the exam. However, it's not obligatory. The second question that we had, very good question, actually. The person wanted to know, actually, this was a question that was asked in different ways from different persons. So I chose the most comprehensive question, the version of it. So it went like this. I would like to know, what are the HF, meaning high frequency operating frequencies, that the technician license, basic class according to the TAT, can grant you for operation in Trinidad and Tobago? So the short answer to that question is that the basic class of license in Trinidad and Tobago does not have any HF privileges at all. In other words, 30 megahertz and below, no privileges in the basic class in Trinidad and Tobago. We have provided some information here on your screen, what the technician class license in the US grants as far as HF. It is some HF privileges, but when we look at what's actually granted under the American system as a technician, First of all, there's a limitation of 200 watts. And a couple of the bands, you do have some privileges there on the HF part of the spectrum. And we'll get into what HF is a little later on in the course, but HF is 30 megahertz and below, or 3 to 30 megahertz. So note that the modes that hams will have on those bands are not generally voice. There is a little bit of voice privileges on the 10-meter band, but it's mainly CW or Morse code and some digital modes such as RTTY. But notice, mainly Morse code, CW. So it's not as though a technician will be able to use voice on most of those bands that they have access to. So just bear that in mind. And note that if you have a technician class license in the US, which will have some HF privileges in the US, as listed here on the screen, that does not translate that you will have those HF privileges in Trinidad and Tobago, okay? So basic class license, no HF privileges. So another type of question that we got was what constitutes an amateur radio station? So we differentiate between an operator license and a station license. And most licenses are operator/station licenses. So that prompts the question, well, what is an amateur radio station? And there may be other definitions, other questions talking about a station. So what exactly is an amateur radio station? So we have a picture on the right-hand side as to what an amateur radio or ham station might look like. You see a lot of equipment, transceivers, transmitters, amplifiers, meters, microphones, even a computer screen, computer connected. Outside of the ham shack, as we refer to this as, will be antennas and so on, right? So that's just a picture. However, an amateur radio station has one or more transmitters, receivers, antennas, and other equipment used to communicate. And note that to legally operate such a station, the operator must hold a valid amateur radio license issued in the case of Trinidad and Tobago by the Telecom Authority, also known as TAT, and in the US, the FCC. So you must have that license to operate legally. Otherwise, you will be in breach, you'll be in violation of the law. And of course, amateur radio stations, as we would have mentioned in the intro session, will be for hobbyists, enthusiasts, rather than professional broadcasters. So it's used for personal communication and experimentation, as well as to give back public service, for example, in emergency communications whenever there's a natural disaster. So of course, like everything else, most services, most hobbies, you can have quite a wide variety of what an amateur radio station would look like in terms of its size and complexity. So one station may have a simple handheld radio, and others may have a sophisticated shack with many radios or many transceivers, antennas, and other types of equipment, as you can see on the right-hand side here. Right? So this is just a slide to give a bit of information on that question as to what is an amateur radio station. Okay, so just a reminder of the material all of the participants online should have received by now an electronic copy or PDF copy of these 4 documents on your screen. The one that we are using directly in the course will be the No Nonsense Technician Class License Study Guide by KB6NU. That's the gentleman's call sign, and that's the book that we'll be using. So everyone by now should have received this via email. Of course, anyone still yet not receiving it or not seeing it in their email, please send an email to the contact later on, as well as you can send a WhatsApp as well. Before the course, please. All right, so we want to just recap a little bit on some of the concepts that we talked about last session. And I have a slide here that talks about the analogy that we have been using from the start. Because we are talking about electronics and the electric circuit, we are using water that most of us might be familiar with to explain and discuss some of the concepts. So note that when we talk about the electric circuit and the water analogy, and we talk about electrons and moving throughout the wires and the circuit, or in the case of the water circuit, water moving throughout, Persons, again, with advanced knowledge of physics and electronics will recognize that we are basically making an approximation. So for those persons, please bear with us. We are trying to gain an understanding at a basic level of the concepts. So while we will talk about voltage and current and resistance, really and truly, it's fields that cause the energy to flow in a circuit. But we will not be getting into that or those topics in the class. We are keeping it at a simple, what we call light touch theory, again, as indicated during the intro. So we just wanted to spend a couple of minutes, again, going over this analogy that we're using, because in the course, we'll be talking quite a bit about circuits and electric or electronic components. So on our right-hand side here, we have a very basic electric circuit that we saw last session. We saw that we had a battery, and of course, we had a load or resistor, and we said there were wires that connected all of these together. And what flows inside of an electric circuit called electrons. And we gave the analogy of a water circuit to understand the concept, where you have a pump, and the pump would sort of be the equivalent of the battery. It's pushing water out into the water circuit, into the pipes. So the pipes are the equivalent to the wires in an electric circuit. And inside of the water circuit, of course, we have water. Inside of the electric circuit, we have something called electrons. That's what's flowing. And of course, we have the equivalent where you have a resistance or load. It could be a constriction in the water circuit, a smaller pipe. Same thing with the electric circuit. So it proves or provides resistance to the flow. So in the case of water, this constriction or smaller pipe will provide resistance to the flow, make it more difficult for that water to flow. Same thing in an electric circuit. The load or the resistor will provide resistance to the flow. And in electric circuit, it's resisting the flow of electrons. In a water circuit, which is the analogy, it's providing a resistance to the flow of water. Then, just to mention, we talked about taps and valves in the water circuit. Well, just to illustrate, on the electric side, we have a switch. It could also be what we call a potentiometer or a volume control knob that varies. So in the same way that a valve in the water circuit can be shut off completely, you can turn it off completely, locked off, and no water will flow. So too in an electric circuit, you may have a switch that when you open that switch, there's no flow of electrons, no flow of current through the circuit. Similarly, in the water circuit, when you close that valve, you turn the tap off, there's no flow of that water in there. So that's the analogy that we're using, the water analogy. So hopefully this will give us a basic idea as to the concepts that we're talking about. And we talked about voltage as the force or the pressure of the battery sending out the electrons into the circuit, just like a pump will in the water circuit. We talked about current being that flow of the electrons in the electric circuit. And we said in a water circuit, there's also the flow of water. We talked about the beach or a river, where you often say, well, there's a current in the river because, it's strong. Or in the beach, you will see a riptide and say the current is strong. So we're using water as the analogy. So folks, hopefully that is helpful to us in understanding the electric circuit. Okay, so we dealt with circuits previously. We talked about some concepts, voltage, talked about resistance, we talked about current. So we're now going to differentiate a couple of types of different circuits that we'll have to deal with for our course. We need to know about them. So the first one we deal with is called the series circuit. So it's an electrical circuit. On the right-hand side here, it's represented on the diagram. It looks very similar to the circuit we used previously, except we have added in a component, an extra component, to illustrate the concept of when we say something is in series, right? So if we were to look at this circuit here, you will notice that you have the battery. So we know that provides a voltage or electromotive force. So there's a voltage, it's trying to push through the circuit, and the electrons will flow, and therefore there's a current that goes with it. But notice we have some loads or some resistances here. We have one followed by another. So when we connect components in that sort of sequence, one into the other, that is called connecting them in series, because the current, the electrons has to flow through one and then flow through the other and complete this circuit. So this is a series connection. And we say that the series circuit is the type of circuit in which current is the same through all components. And if you think about it, because the electrons have to flow through both of these, the current has to flow through both of these, the current is equal. Just to let you know, the voltage is different across the loads, just by the way, and we put that as extra information here for you. So we say the voltage. Notice sometimes we will use E or V to represent voltage. E as in electromotive force, or just simply V as voltage. The voltage is different across the two resistors, and we'll come again to what resistors are. But for now, note how they are connected, because we want to compare and contrast another type of circuit. So this is our series circuit. We have our battery connected in series with one resistor, in series with another resistor, and the wire completes the circuit. So that's a series circuit. Note, the current is the same throughout the entire circuit. So now we come to another type of circuit. So we need to compare and contrast to what we just did as the series circuit. And you may already see the contrasting difference. So let's go back to the series circuit. This is what it looks like. Now this is the parallel circuit. So you probably already saw, but wait a minute. There's a branching going on, right? It's not series connected. So when a circuit looks like this, so we have taken our two resistors and they're no longer following one another, one into the other. There's a little branch. So what this means is that there are multiple paths for the current to take. So this is our battery. Again, it's pushing the electrons through the circuit. There's a current flowing, but when it gets to this point, again, we talk about conventional current flow, which goes from positive to negative. It gets to this junction. It has two ways to go. It can go this way, and it can also go this way. So it splits, and that's what makes this circuit a parallel circuit, as opposed to the series circuit. Notice it goes through one. It has to go through this one and then go through this other one. Whereas in the parallel circuit, it goes here and can go to both directions one time. It splits. So some of the current goes this way, and some of the current go this way. Some of the electrons flow in this direction, and the others flow in this direction, because they're all being pushed, and they're trying to come back to this side of the battery. Remember, the battery is like a pump. Remember when we use the water analogy? It's like a pump pushing the water through the circuit. When it gets to this dot here, this blob, that's a junction. And at that connection point, it splits into two directions. So that's why the current is different in each branch of the circuit, because the current is splitting into two, but the voltage, both resistors see the same voltage. That's some extra information, but for the exam, you need to know that in a parallel circuit, type of circuit that you're seeing on your screen, the voltage is the same across all components, right? The current is different, however, but you need to know that the voltage is the same across. So again, let's do a wrap-up diagram that compares and contrasts. On your left-hand side, we have the series circuit that we just looked at. On the right-hand side, we have the parallel circuit that we just looked at. So again, comparing and contrasting, how can you tell a series circuit versus a parallel circuit? Series, one component into the next. Sort of daisy chain, one right into the next. Whereas in a parallel circuit, if you think about it, if you think of the concept of the word parallel, here it is, parallel lines. So this is a parallel circuit. What we need to know for the exam is what the circuit looks like, as well as the fact that the voltage for the parallel circuit is the same. And in the case of the series circuit, the current is the same. So current same for series, voltage the same for parallel circuit. Right. So we talked a bit about needing to have a formula apart from diagrams to represent quantities. So here on our right-hand side, we have a trusty direct current circuit, but we are going to introduce the concept of power. So let's talk about power a little bit. Those in Trinidad and Tobago might have heard the electricity service, TNTech. Always say TNTech, the power to make it work. When we are looking at a light bulb, if we're looking at an incandescent light bulb, we may say that's a 100 watt bulb, or we may say that's a 60 watt bulb. That's the power consumption that those bulbs are using. You may have a 12 watt LED bulb. So we may be familiar with the term power as it's used in the electrical sense. So the term that is used to describe the rate at which electrical energy is used is power. So the rate at which we use that energy, again, it's electrical energy. The rate at which it's used is called power. We are consuming power, and most of us will pay a light bill for the amount of power we use. So power, very simply, we use the letter P to represent power. So we should be able to remember that, P for power. And like I mentioned before when I was talking about the light bulbs, that it's measured in watts. Electrical power is measured in the unit known as the watt or watts. So when we're talking about a light bulb, we say the amount of power it uses is 100 watts. So power is measured in watts. We use the letter P for power, but the units are watts. Just like for voltage, it's volts. You may recall that for current, it's, what is it? Amperes. And you'll be quite right. And of course, what's resistance? The ohm, right? Remember Ohm's law. So when we're talking about power, it's P for power, and the unit is called the watt, right? The symbol for watts is W. The formula, of course, like everything else, we had Ohm's law formula. We have a formula now to calculate power. And you may find that the formula looks quite simple and similar to Ohm's law. You may also find it's a very easy formula to remember. The formula to calculate power in an electrical circuit is P, which is power, is equal to I multiplied by E. But what is I and what is E? Do we know? Well, we should know, because when we did Ohm's law, we knew what I was and we knew what E was. So we're saying P, which is power, is equal to I. What was I? I was current. Yes. And folks, what is E? All those who said it's the voltage would be quite correct. So power is equal to the current multiplied by the voltage. Sometimes you'll see this formula written the other way around. P is equal to EI. But I wrote it in this way because when we write it this way, P is equal to IE, it spells the word pi. Some of us love pi. So one way to remember the power formula is to think of a pi, or the power pi. P is equal to IE. Once you remember that pi, then what is P? Power. What is I? Well, I is current. And what is E? E is the electromotive force or voltage. So that's our power formula for DC circuits. And we will get into some calculations just now where we similarly that we use Ohm's law to do some calculations. As amateur radio operators, we must be able to do some calculations as well. All right, so we'll do a couple of slides and then we'll take a short break and we'll come back with the rest of the slides. Okay, so let's do a couple. So we're talking about power, and we just discussed that there's a formula to calculate the power. Once we know the current and the voltage, we can calculate power. So here's a worked example, and this is an actual question in your exam. So the question is, how much power is delivered by a voltage of 13.8 volts DC and a current of 10 amperes? So we have dissected this question a little bit by highlighting some of the key words in there. So what are they asking us? How much power? So you know you need to end up with an answer that says power equals something. So that's why we dissect these questions to understand what are they asking us, because these questions can seem pretty long. It could seem kind of confusing. What is this question about? But we know here they're asking us how much, what? Power. And then I say to myself, but wait a minute, I do know that power formula. I know pi, P-I-E. P is equal to I multiplied by E. So I am sure I can calculate power. But what are they giving me? Are they giving me all I need to do the calculation? Let's see how much power. And they tell us the voltage of 13.8 volts. Rather convenient. That is E. They have given us what E is. E is the voltage. And then now, what else have they given us? They say the current of 10 amperes. They have just put it in our lap. They have given us all of the information that we need to calculate power, because we know the formula for power is P is equal to I multiplied by E. Remember that little aide de memoire, pi, P-I-E? Right. So all we need to do now is substitute for I, which is the current, and substitute for E, which is the voltage, which they gave us in the question. They basically gave us the answer. All we have to do is calculate it out. So P is equal to I multiplied by E. P is equal to, well, we substitute now. So we have I. What is I? I is 10 amperes. So we stick that 10 in here. That's how we get 10. We replace the I by 10 multiplied by E. What is E? E is voltage, 13.8 volts. So we stick 13.8 there. So we end up with a straightforward equation. P is equal to 10 multiplied by 13.8. We might be able to do that in our head. We may need to use a calculator. When you multiply that out, you get P is equal to 138. But 138 what? Yes, 138 watts. So again, certain things have units, and we need to respect the units. So it's P is equal to 138 watts. And folks, this is an actual question in the exam. And we're just putting a circuit here to represent. So when we are doing these formulae and calculations, we could sort of make it real and say, you know, this is a circuit. There's a voltage caused by a battery. There's a current flow, conventional current from positive to negative. And there's a load somewhere inside of there. And of course, there's power dissipated over that load. And if we want to calculate the amount of power dissipated by this load or resistance, we can use the power formula. So let's do another example. So, right, so it was nice we do it twice. So it says here, next question, again, an actual question in the exam. How much power is delivered by a voltage of 12 volts DC and a current of 2.5 amperes? Again, very similar question to the previous one. What are they asking us? As we have dissected this question, they've asked us how much power. So we know they're asking us for power. We need a formula for power. Power is equal to something. Do we have such a formula? Yes, that's P is equal to IE or pi. So we know we're going to be using that formula most likely. And let's see what they have given us to see if we could use that formula. They have given us, it says delivered by a voltage of 12 volts. So voila, we have E. E is the voltage. And they have told us a current of 2.5 amperes. Yes, are they making life simple for us? Yes, they're giving us everything that we need. They have given us the voltage, they have given us the current. So let's use our trusty formula. We write the formula down. P is equal to IE. We remember it because remember power pi. And then now we think about what is P? P is power. What is I? I is current. So we are looking for something in amperes. Did they give us that? Yes, here it is. 2.5 amperes. E. What is E? Electromotive force. That's in volt. That's measured in volts. So we're looking for voltage, 12 volts. So let's now substitute in this formula just like we did before. P is equal to I multiplied by E. We have P is equal to, well, I. What is I? The current, 2.5 amperes. So we stick 2.5 amperes in the formula, replace I. Then we replace E by the voltage, 12 volts. Here's the 12. That's how we got it. P is equal to 2.5 multiplied by 12. Add in your head, write it down, or use a calculator, you'll get 30. P is equal to 30, but 30 what? Remember, power is measured in watts. So P is equal to 30 watts. And that's how we get this answer right there. So folks, let us take a 2-minute break and we'll come back with some more calculations. Please get up. Take a little stretch, maybe have a little glass of water, a bathroom break, and we'll be right back. 2 minutes. All right. So, yeah, good evening there, Junior. Great to have you, Charlie. Hi, how you doing? Um, okay, Stefan, sure, certainly welcome. We try to break it down as best as possible, so appreciate your feedback. Okay, Anton, yeah, there are a couple of suppliers locally that do sell amateur radio equipment, so we can probably provide that information as well, subsequently, of course. All right, so let's continue from where we left off, folks. All right. So as you see for yourself, the mathematics should be quite accessible to us, the type of calculations we're doing. It's kind of almost the same if I'm buying 10 oranges at $2 per orange, the total price is $20, price is equal to quantity time in unit price. So that's the sort of maths we're using here. So hopefully this is accessible to us all and not posing too much difficulty for most of us, right? So let's try to keep it as simple as we can. All right, so I did promise you some more worked examples, formulae, and so on. So you would probably have guessed that seeing that we have a formula P is equal to I multiplied by E, sometimes we may have a situation where we may not have some of those quantities, or we may not have one quantity. We may have power. We may not have another quantity like current or voltage. So just like Ohm's law, we can use algebraic manipulation and move the terms around. So when we want to know power or calculate power, and we already have the other two terms, current and voltage, that's P is equal to IE, all well and good. But what if we want to find out the current if the power is known and the voltage is known? Well, the formula is in this format here. You can use your algebra and move the terms around and get I is equal to P over E. And if you're wondering, do we have a similar method to what we talked about last week coming up? Next slide. Yes, we do have a way, again, to remember it. So two ways. You can use the algebra. The other way is a nice little aide de memoire again. And of course, if we wanted to find out the voltage or the electromotive force, E is equal to P over I. So let's look at our easy to remember. All right, does this look familiar? Well, yes, it's the ever popular Amaus plate. And we have gotten some pretty good feedback from the participants in terms of remembering it, right? So if we don't wish to do the algebra, we can just draw this plate, a circle and then a T, divide it in half and then that part in half. So you just put a T inside the circle. And you spell pi, P-I-E, right? And once you do that, you can work out any term. You can say P is equal to, what is it? Well, I, and I is next to E, so that means multiply. I multiplied by E, it's never minus or plus, right? And then if I want to find out what I is, I want to see I is equal to something. Well, I is equal to, well, P, and P is on top of E. And P on top of E means P divided by E. So I is equal to P over E. There we go. And what if I wanted to find out E? Well, E is equal to P over I, or P divided by I. And here I'm sorry, we have a little error on this slide here, folks. We'll correct it for the next session. This should be E is equal to P over I. So little error on this slide. But you get the point, folks. This is a nice aide de memoire to understand the power formula, similar to Amaus plate for Ohm's law. You can draw this and derive your term as you require. So let's do a couple of worked examples. All right. So again, real question in the exam. How much current is required to deliver 120 watts at a voltage of 12 volts DC? Now, they didn't ask us here to calculate power, did they? They are asking us, let's dissect this question. What do they want? What do they want to find out? How much current? So we need a formula or an equation that's in the form of current is equal to something, because that's what we have to calculate. That's what we have to derive or find out. But do we know such a formula? Well, maybe we do. But let's see what they gave us. They're asking us to find the current. Remember, current is I? Yes. But they have given us watts. They have said deliver 120 watts. But we know watts represent, what does it represent? Yes, you're quite correct. Watts represent power. So they have told us what the power is, 120 watts. What else have they told us? They have said at a voltage of 12 volts. So they have given us the voltage. So they want to find out the current, and they have given us the power as well as the voltage. Can we find that out? Well, let's go to our adapted Amau's plate. Yes, we want to find the current. So we say I is equal to P divided by E. Here's our formula on this side here. So that's the form that we need to use. And here it is. So we use the formula I is equal to P over E. So we have the formula. All we need to do now is substitute the values into this formula. So we can get I, which is the current, is equal to something, whatever that something is. So we look at P and then we look at E. So what is P? P is power. They give us that 120. So we replace the letter P with 120. So that's how we got the 120 on top of here. That's the numerator. Then we have to replace E with a value. E is what? Voltage, electromotive force. They have given us that as 12 volts. So we replace E here with 12. So that's the denominator. So we have to divide now 120 by 12. And we get 10. So the current I is equal to 10. But 10 what? Well, the units of current is the ampere. So I is equal to 10 amperes. So again, just a little circuit on the side to give us an idea what we're doing here. They have given us the power, they have given us the voltage, and we want to calculate the current in this circuit. Right. So that's it for calculations for the moment. Let's go now into the magnitude prefixes and some conversions that we need to learn and understand. For us as amateur radio operators, we will encounter terms that we need to convert, and we need these prefixes and we need to understand these prefixes, but we are probably likely already familiar with them. So for example, we may already be familiar with a meter, right? So we'll say a 1 meter rule, or something is 3 meters wide or 10 meters tall. But then if we are giving a longer distances, we may say something is 10 kilometers or 10 kilometers, depending on how you want to say it. So 10 kilometers, we may have 3 meters. And similarly, just like we have the base unit meters and then kilometers or kilometers, you can have other higher powers or other higher magnitudes. So this is what we want to discuss here this evening. You have a base unit such as the meter, and you will have a symbol M for the meter. But you may also have a kilometer or kilometer, which is 1,000 meters. But not only do we have kilo as the prefix to mean 1,000, we also have mega, which means 1 million. And we have giga. Also, this is increasing power from the base unit, but we also go the other way. So we go 1,000th of something is milli, right? 1 millionth of something is micro, and so on. We have nano, pico. So all of these are the magnitude prefixes. Again, we may be familiar with some of them already. So for example, you might have heard a micro USB port, you know. So these terms should not be entirely strange to us, but we need to discuss them in terms of our calculations, our electric circuits, and how we do our representation of the values. So this is a handy table. I'll encourage us to all get familiar. So we have the prefixes, what they're called here, giga, mega, kilo, milli, micro, nano, pico. And then the abbreviation. So for giga, it's capital G. For mega, it's capital M. For kilo, it's lowercase k. For milli, it's lowercase m. For micro, you can either use the U, the little letter U, or lowercase u, or if you can type the letter mu, which is a Greek letter, mu, all right? Of course, nano is N. Sorry, again, we have a little error on the slide. And pico is P. So we'll correct this slide for you folks. We also wanted to give an idea when we said 1,000, million, 1,000, 1 million, and so on, what those numerical numbers look like. And those who are familiar with the exponent notation, 10 to the power of 0, which is the base unit, 10 to the power of 0 is 1, right? So base unit, 10 to the power of 3, which is 1,000, 10 to the power of 6, 1 million, and so on. And of course, you go in the other way, reciprocal. So you have 10 to the power of -1, which is 1,000, 10 to the power of -6, for those who are familiar. So not necessarily to learn, but these are just references, just in case you're familiar, so that you could reference to what you have as prior knowledge. And of course, we gave some examples here. As base unit, we'll have the meter, we have the kilometer. And of course, when we go with mega, and as radio operators, we will be hearing a lot about megahertz and kilohertz and gigahertz when we talk about frequencies. And we'll see that we're probably already familiar with it, whether we knew it or not. So you have millimeter, microfarad, nanometer, picofarad, right? So we have a little table here that we'll be using, that if you want to go from one unit to another, how do you do that? If you're going down, you have to multiply by 1,000. And if you're going up, you have to divide by 1,000. So this is what this table is intended to. Again, we'll fix the little error that we have seen here on this table for our next class. All right, so let's actually do a worked example. Right. Let's do a worked example. So the first one, and this is an actual question in the exam. How many milliamperes is 1.5 ampere? All right. So let's dissect this question. What are they asking us? They're really asking us to convert, They want to know how many milliamperes is 1.5 amperes. So they're giving us 1.5 amperes, but they want us to express this in milliamperes. So let's go back to our table. We want to go from amperes to milliamperes. Let's see how we do that. So we are the base unit amperes, and we need to go to milliamperes. So let's check that. Yes, so give us amperes. We need to go to milliamperes. How do we do that? So according to our trusty table, this is the base unit, and we need to go to milli. So from the base unit to milli, we are going down. So let's cross-reference this table, convert down. What do we need to do? To go down, we need to multiply by 1,000. So any step to go down from one to the next is multiplying by 1,000. Yes, multiplying by 1,000. If we are going up, we have to divide by 1,000. That's what these two columns here. Anytime you're moving up, the prefix is you divide by 1,000. Anytime you're going down or you're converting downwards, you multiply by 1,000. So we're moving down. So therefore, we need to multiply by 1,000 because we're just going from one base unit to the milli, which is right next to it. So we just multiply by 1,000. We'll see a little later on if we have to do a multiple jump. Each jump is 1,000 you're multiplying by going down. Multiply by 1,000. If they wanted micro, after we multiplied by 1,000, we need to multiply by another 1,000, and so on. If we're going up, we divide by 1,000. And if we go up again, we divide by another 1,000, and so on. So hopefully this is helpful. Right, so we have just determined that to go from amperes to milliamperes, we need to multiply by 1,000. And we just sort of excerpted a little piece of that table here for us, right? So multiplying by 1,000, they give us 1.5 amperes. So we put that down, 1.5. We are multiplying by 1,000 to convert it to milliamperes. Here's the 1,000. And we end up with 1,500 milliamperes. So that's the answer to this question. Let's do another conversion example. All right. So we may remember we talked about the hertz when we said frequency. And we may be thinking, well, I'm not familiar with hertz. Well, let's get familiar with the hertz. In amateur radio, we'll be talking about hertz quite a bit because we are putting in frequencies on radio equipment. We are tuning a dial to a frequency. And of course, frequency is measured in hertz. So they have said to us here to convert 1,500,000 hertz to kilohertz, right? So what are they asking us to do? They're asking us to go from hertz to kilohertz. So let's go back to our trusty table. So hertz will be the base unit, but they want us to go up to kilohertz. Remember we said when we're going up, each step is divide by 1,000 to convert up. So we're seeing here that to go from base unit to kilo, we need to divide by 1,000. So that's what we need to do. So they give us 1.5 million or 1,500,000 hertz. So we put that down. Our trusty table says we're going up, we need to divide by 1,000. So we put the 1,000 in the denominator. When we divide that, we get 1,500 kilohertz. So we have just converted from hertz to kilohertz by dividing by 1,000. Let's do another example. Right, so we know about volts, right? So they said convert 1 kilovolt to volts. So let's see, how do we do that? Let's go trusty table again. So they told us that we have 1 kilovolt, right? So we are the kilo level here, and we need to go to volt, which is the base unit. So we're going from kilovolt to volt. When we go down, what do? We multiply by 1,000 according to this table. Is that what we need to do here? Yes, we are converting from kilovolts to volts. So it's 1 kilovolt. So we write down 1 to represent 1 kilovolt. And then we are multiplying by 1,000 because we are going down in the table, multiplying by 1,000. 1 by 1,000 is 1,000 volts. So hopefully we are getting an appreciation for the idea of converting from one unit to another magnitude. All right, let's do another one. This time we are dealing with micro and volts. So we are jumping here now. You see, remember we said that we can jump from different levels as well. It doesn't have to be just jumping one level to the next. We can jump multiple levels. So this is an example. They have asked us to convert 1 microvolt to volts. So let's see what they're asking us to do. Micro to volts. So volts will be the base unit, and they're asking us for microvolts. So let's see. Trusty table. So we're here. We're converting from the microvolts. So micro to volt. Well, let's go up. We want to go up to the base unit. But between the base unit, we have milli. They didn't ask us for milli, so we have to go up again. We are looking at the base unit for volt. So we need to go from microvolt to the base unit of volt. But we have to do 2 jumps. So we have to divide by 1,000 and again divide by 1,000. So we are divided by 1,000,000. So let's see. So we have 1 microvolt. So we write that down. And we divide by 1,000,000. Why are we divided by 1,000,000? Because we are making 2 jumps. Remember, to go from one jump in our table to the next, we divide by 1,000. And then we divide by another 1,000. So 1,000 by 1,000 is 1,000,000. So that's how we got 1,000,000 here. We could have easily just divided it by 1,000 first, and then divided it by 1,000 again, right? But we did it kind of shortcut way. We just decided to divide it by 1,000,000 because we know 1,000 by 1,000 is 1,000,000. So the answer that we get, 1 over 1,000,000, is 1,000,000th of a volt. That's the answer. Let's do another one. Magnitude conversion, this time milliwatts to watts. So we're going, let's go to our trusty table. Milliwatts to watts. So watts will be just the base unit, right? There's no prefix. So milliwatt to watts. So we're going up, and therefore we are expecting to divide by 1,000 because we're converting upwards. Milli to watts. Let's see. Right. So we're converting 500 milliwatts to watts. We know we have to divide by 1,000, so we write down the 500 milliwatts, and then we divide it by 1,000 to convert up from milliwatts to watts. That's what we're doing. We're going up. When we divide that, we get 0.5 watts. Okay. Let's do one more again. All right, these are actual exam questions, folks. So that's why we're going through. Remember, we said we are tackling every single question in the question pool. So we're doing it so that we can get very familiar. So when we go to the question pool and we see these questions, it's like, yeah, we know how to do that. We have calculated it before. So next question. They want us to convert 3,000 milliamperes to amperes. So let's see what we're doing. Trusty table. So we want to go milliamperes to amperes. So again, there's no prefix in amperes, so it's the base unit. So milliamperes to amperes, we are going up. We divide by 1,000. So we're not going down. They didn't tell us to go from milliamperes to microamperes or nano or pico. They didn't tell us to go from milliamperes to kiloamperes, megaamperes to giga. They said, let's go from milliamperes to amperes, and amperes is the base unit. So we're going up and we are dividing by 1,000 because we are converting up. Let's do that. So they want us to convert 3,000 milliamperes to amperes. So you probably already wrote that out in your head, but let's write it down. 3,000 milliamperes. We're dividing by 1,000 because we're converting up. When we calculate that, we get 3 amperes. Okay, so on your screen on the right-hand side, there's a picture of one of the older types of radios, broadcast radios, AM, FM radios. A dial that some of us may be familiar with. We have the digital equivalent now. Broadcast radio. Back in the day in Trinidad and Tobago, we had radio 610 and 730 and probably others. And of course, on the FM dial, 95.1, 97, 100.1, and so on, 94.7. Those are frequencies. But have we ever wondered, it's 95.1, what? What is it? Is it amps? Is it watts? Is it ohms? No. It's hertz, and it's actually megahertz. And the AM dial, it's not 710 watts or 710 amps. It's 710 kilohertz. So we just put this diagram up to show that we probably already knew these terms or came across them, just never paid attention to them. So in our quest as radio amateurs to understand the terms and the quantities that we use, frequency is a key term, and we'll be hearing it very regularly throughout the rest of the course and the various levels. So the question in the question pool is, what is the abbreviation for kilohertz? So we said in our last session that hertz is what we use, the term we use to represent frequency, but they want us to abbreviate kilohertz. And we showed it right here on your screen on our radio dial. This is a regular broadcast radio. We saw kilohertz abbreviated as KHZ, but notice the case is important. K, the prefix that we showed in our trusty table, the abbreviation for kilo is small k or lowercase k, not capital K. Although you will see that from time to time, that's an error. That's not proper. We are learning proper thing here, folks. So the prefix for kilo is K. So we know that's a prefix, but they want kilohertz. What is the symbol? Well, how do we represent hertz? It's abbreviated as HZ. And notice the capital or the uppercase H in HZ. So when we put them together, we get lowercase k, uppercase H, and lowercase z. So KHZ. That is the abbreviation for kilohertz. And again, we probably already know what kilohertz is. If you have ever tuned to an AM dial, you might have just not paid attention to this on the side, KHZ, kilohertz. So it's 710 kilohertz. All right, so we now come to another similar question. What is the abbreviation for megahertz? Again, hertz is the unit of frequency. Again, similar dial 95.1 FM, popular radio station, but that's 95.1 megahertz. So we already know this stuff, folks. So they're asking us, what's the abbreviation for megahertz? We already know, but let's work it out. The prefix for mega is M, capital M. Let's check our trusty table. That has one inaccuracy. So mega, the abbreviation is capital M. There it is, mega M. So we know we have to use capital M. uppercase M. So the prefix for mega is M. And we also know that hertz is abbreviated as HZ, capital H, lowercase z. So when we put them together, we get megahertz as MHZ, capital M, capital HZ. That's how we represent megahertz. Again, we are probably already familiar, having seen it on a radio dial. It's not a stranger to us. So let's do a little conversion again. So the question in the question pool is, they have given us a frequency and told us to convert it. They said, convert 3.525 megahertz to kilohertz. Whoa, what are they asking us to do here? Convert megahertz to kilohertz. Let's see how we do that. Trusty table again, megahertz to kilohertz. So we are here, we are at the megahertz level. And they want us to go to the kilohertz level. Well, that's one level down. And we know when we convert down, we multiply by 1,000. So to go down, we have to multiply by 1,000. Let's do that. So we are converting 3.525 to megahertz to kilohertz. So we are multiplying by 1,000. So we take the 3.525 or 3.525 multiplied by 1,000 to convert it, and we get 3,525 kilohertz. Folks, it's as simple as that. Let's do another one. They've asked us to convert 28,400 kilohertz to megahertz. All right, what are we doing? Kilohertz to megahertz. Let's check our trusty table. Okay, what are we doing again? Let's see here. We are converting kilohertz to megahertz, all right? So we are going up, kilohertz to megahertz. So we are at this level, kilohertz, at the kilo level, and we go into megahertz. We are going up. What do we do when we go up? We convert up, we divide by 1,000. Anytime you're going up, you're dividing by 1,000 if you're jumping one level up. So let's go back. So we are converting kilohertz to megahertz. Here we go. And we are dividing by 1,000. So the frequency of 28,400 kilohertz, we put it on, write it down. And then to go to megahertz, we divide by 1,000. So that becomes the denominator. Use our calculator or manually, and we get 28.400 megahertz. So that's the calculation. Shift the decimal point to 3 spaces to the left. 28.400 megahertz. Let's do another one for good measure. They want us now to convert a frequency of 2,425 megahertz to gigahertz. What are we doing? We are going from megahertz to gigahertz. Let's see how we do that. Mega to giga. Check our trusty table. Mega to giga. So we see they're next to each other. So we're going from mega to giga. We're going up. So we know by now, anytime we are going up, we have to divide by 1,000. See if that is true. Okay. Mega to giga, we divide by 1,000. So they have given us 2,425. We write that down. We divide by 1,000 to go up in units. And we end up with, again, 3 decimal places to the left, 2.425 gigahertz. Let's do one again. Now, we may not have come across the unit called the farad. That's measures what is called capacitance. So we'll come to what capacitance is in a future lesson. However, let's just go with the flow. So they've asked us to convert 1 million picofarads to microfarads. Ooh, all right. Where are we going from? We're going from pico to micro. Pico to micro. So let's go. Pico to micro in our table. So we're going from pico to micro, but are we going up? Yes, we are. Are we only going up one level? No, we're not. We're actually going up 2 levels. So we have to jump from pico to nano to micro. So notice we said in this table, every time we go up 1 level, we divide by 1,000. So we have to do that twice. We divide by 1000 and divide by 1000 again. So here we go. So we are converting 1 million picofarads. So we write that down at the top, or the numerator, and the denominator is what we're dividing by. So we need to divide by 1000 and then divide that by 1000 again. So we can do that very quickly. 1000 by 1000 is 1 million. So we can just simply divide by 1 million. Or we could have done it in 2 steps. We could have taken the million and divided by 1000. We would have gotten 1000 from that, and then we would have divided by the other 1000, and then we would have ended up with the same answer, which is 1. 1 what? Well, microfarads, and this is how micro is represented. So again, we'll talk about the farads on our next class. So folks, let's get straight into the question pool questions for all of the theory we have done this evening, and that will call a wrap. So let's go to our question pool, the no nonsense guide. And let's deal with these questions very quickly. We have dealt with all of these theories and all of these questions, so we should be able to push through pretty fast. Again, this is just to show you in the real exam what the question looks like. You'll see the distractors or the wrong answers as well for reference, but we have covered all of this. So let's go. In which type of circuit is DC current the same through all components? So they're asking us for the current being the same. And we had learned that that refers to a series circuit, not parallel, series. Any doubt? Look over the theory, please. All right. So next question in the question pool. In which type of circuit is voltage the same across all components? Notice the previous question, they asked us about the current being the same. This one, they have asked us about the voltage being the same across all components. We learned that it's the parallel circuit that the voltage is the same. Okay, we're coming to now some power questions. So they've asked us, which term describes the rate at which electrical energy is used? Remember, TNTech, power to make it work. So that term is power, the rate at which electrical energy is used. All right, so that's the TNTech question. Please, for those in Trinidad and Tobago. All right. Okay, next one. Electrical power is measured in which of the following units? What units? Yes, it's the watts. Electrical power is measured in watts, not volts, not amperes, and so on, right? Okay. Which is the formula used to calculate electrical power? So remember we said power, pi. Of course, they write it down a little bit differently here in the exam. P is equal to E multiplied by I. So that's the answer. Next question in the question pool. How much power is delivered by a voltage of 13.8 volts DC and a current of 10 amperes? Well, we used our power formula and we multiplied 13.8 multiplied by 10 because P is equal to IE. That's what we used to come up with the answer 138 watts. Next question in the question pool. Again, we covered all of these during the theory. How much power is delivered by a voltage of 12 volts DC and a current of 2.5 amperes? So they are asking us power. What is the power? They have given us the voltage of 12 volts and the current of 2.5. So we also use the power formula. P is equal to IE, multiply the two, and we get 30 watts. Next question. How much current is required to deliver 120 watts at a voltage of 12 volts DC? So this is also the power formula, but they have given us the power and they've given us the voltage. And what we have to calculate is the current. And through algebraic manipulation, we got the form of I is equal to P over E. So we divided the two, 120 divided by 12, and that's 10 amperes. Okay. All right, so similar table to what we dealt with here. All right, we just dealt with this question a couple of moments ago. How many milliamperes is 1.5 amperes? Well, we know that we are multiplying by 1000 to go from milli to amperes. So the answer is 1500 milliamperes. just cover this, folks. Which is equal to 1,500,000 hertz? So that's really asking us to convert hertz to something. So the correct answer here, it's not 1,500 megahertz, neither is it 15 gigahertz or 150 kilohertz. It is 1,500 kilohertz. What is equal to 1 kilovolt? So we have to look at the answers and see which one of them is true. Again, we did that calculation a little earlier. 1 kilovolt is 1,000 volts. That's the answer. Next question. Which is equal to 1 microvolt? So the answer to that question, we worked it out in the slide, is 1/1,000,000th of a volt. So that was to convert from microvolts to volts. It's not 1 million, and it's not 1,000 kilovolt, and it's not 1/1000th of a volt. It's 1/1,000,000th of a volt. Okay, so just go over the theory, folks. The slides are provided to you as well as the recording. Once it sticks, feel free to look it over for the calculations. We're just kind of going through very quickly these questions in the question pool. Which is equal to 500 milliwatts? So they're asking us to convert from watts, milliwatts to watts. It's not of these in gray, it's 0.5 milliwatts to watts. We are dividing by 1,000. Next question, which is equal to 3,000 milliamperes? So this question is asking us to convert from milliamperes to amperes, and we know that we need to divide by 1,000 to go from milliamperes to amperes, and the answer is 3 amperes. Next up, what's the abbreviation for kilohertz? So notice how they're trying to tie us up. They put capital K, capital H, capital Z. We know that's not true. They put lowercase k, lowercase h, lowercase z. That's not true. They put lowercase k, lowercase h, and capital Z. We don't know about that. What we know about is lowercase k for kilo and capital H and lowercase z for kilohertz. All right. What is the abbreviation for megahertz? Again, we know it's capital M for mega, and again, H, capital HZ, so MHZ. So notice all of these are wrong. It's not capital M and lowercase h and z. It's MHZ, capital M, capital H, uppercase M, uppercase H, lowercase z. All righty. Which is equal to 3.525 megahertz. So they're asking us to convert from megahertz to kilohertz. Here we go. To do that, we have to multiply by 1,000 and we get 3,525. Next question in the question pool, which is equal to 28,400 kilohertz. Well, they want us to convert to megahertz, so we have to divide by 1,000. So we get 28.400 megahertz. Okay, we're coming to the end soon, folks. We're almost there. Which is equal to 2,425 megahertz. They want us to convert from megahertz to gigahertz. So, of course, to convert, what we need to do is divide by 1,000. So we end up with 2.425 gigahertz. And the last question in question pool that we'll cover for this evening's class is which is equal to 1 million picofarads. So again, we'll deal with what the farad is. Of course, we have a little note here in the question in the no nonsense guide. The farad is the unit of capacitance. All right. So 1 million picofarads, we need to convert that to microfarads. Right. So we divide that by 1 million because we have to divide it twice by 1,000 and we end up with 1 microfarad. We just work that out. So folks, let's just return to the slide deck quickly. Just again to remind folks, we are having a webinar coming up on Saturday, the 13th of May. We're hoping that each and every one of you can join us. It's the role of weather in being disaster ready. We will be reminding the team about this upcoming webinar. It should be pretty interesting. Distinguished panelists to tell us about the weather. Again, if you have any questions, feel free to pop them via email, or you can send a WhatsApp to this number on your screen. We'll do our best to answer the questions. Let's see quickly if there are any questions that we can answer quickly here. All right. Okay, Anton. Yeah, we'll get back to you with respect to suppliers. Anthony. Yeah, so you can actually purchase a starter handheld radio from Amazon for about $25 US. Yes. All right. So you can start at a really competitive cost. Yeah. All right. Okay, Anissa, sorry about the audio issue on slide 16. We'll see what we can do. All right. Yes, Junior, you can take a calculator, but no tables. Just a pencil calculator. You can take some blank paper in to write on, or they will give you blank paper, but not tables of any kind. You cannot work with any book or reference material. So some of these things you need to memorize. At least try to conceptualize it. Yeah. Yeah, no problem, Samuel. Glad to have you there. Hopefully the recording sticks. You'll be able to catch everything. Yeah. All right. So I think we have some other questions. Is that a Raspberry Pi implemented such as Raspberry Pi? Yes, I've had quite a bit of experience using Raspberry Pi for amateur radio. Right. So shortwave as opposed to long wave, medium wave, right? So we will, in the subsequent sessions, we'll be defining the various meanings of the various bands, such as long wave, medium wave, short wave, as well as HF, VHF, UHF. So Sylvester, more to come on, sorry, Jason, more to come on that. Anthony, yeah, so I got you with Raspberry Pi. Yeah, feel free to email Adish. Okay, cool. Have a good night as well. And again, thanks, Adish, as well as Edward, for pointing out the audio issues last week. Hopefully, I'm hoping it's a marked improvement. So you can always drop me a line and tell me if this audio it should be significantly better, I'm hoping. So thanks a lot for the feedback, folks. Yeah. All right, I think that's it to the questions in the chat. So feel free to hit me up, any email or WhatsApp for any further questions. Now, folks, I need to let you all know, we should have our class next week, Friday, the 5th of May at 8:30 p.m. However, please stay close to your email. I'm not sure if where I'll be, I'll have good internet access. So I will know by Monday what that internet access is like, and I will shoot you guys off an email if we need to postpone for any reason. But it is still on as is, but that's why I have an asterisk next to the date. I do suggest that you check your email as regularly as you can, please. Certainly before the class. Don't want to have any disappointments. We do send out at least one email to your email every week. If you're not getting it, please let me know. First, check your spam folder. It may go inside of there. All right. So thanks, everyone, for the extra time as well. And be safe. Take good care. And do have a good night.